Welcome to today's tutorial. Let's get started. Let's have a look at our agenda for today. Today we're looking at the Cscape shift register instruction. We'll start with what is the shift register. Then we'll look at how they're used in automation and what shift register instructions are included in Cscape. We'll also talk about different applications where you can use shift registers. We'll have demonstrations throughout, and as always we'll finish with a Q&A session. So what is a shift register? A shift register is a register or series of registers that is designed to allow its contents to be shifted left or right. Functionally, shift registers serve as either data storage spaces or data movement devices. As a data storage space, shift registers are valuable in applications such as data logging and mathematical operations. As data movement devices, shift registers are valuable in applications where you're having sequential operations that you need to track. Let's look in more detail now at how shift registers are used in automation. Let's talk first about the use of shift registers as data movement instructions. One example is an application where you need to track a product as it works its way through a machine or a process, or an application where you are sorting dissimilar products that share the same material handling equipment. When using shift registers as data storage instructions, one example could be for high-speed data logging. If you want to capture and log processed data quickly, for example, for every single scan for short bursts of activity so you can analyze that data later. Another example would be to capture historic data so you can periodically examine and manipulate the data using other instructions and logic. What shift register instructions are available in Cscape? First, you have Bitwise instructions, which you can find under Bitwise operations in the project toolbox. Under Bitwise operations, we have 4 instructions that come under the topic of shift registers. Those are shift left, shift right, rotate left, and rotate right. If you also look under move operations, you'll see we have element shift and element rotate, which are also applicable to today's topic. Let's look in more detail at those bitwise instructions, starting with a shift left. What does that instruction do? That instruction operates on the bits in either a word or a double word variable. The first input to that function is the word variable that contains the string of bits that need to be shifted. N is the number of positions that we want to shift those bits. Usually that number is 1, but it could be something else. The output is the variable containing the result of the shift, so that bit pattern after the shift is copied into the output. So when shifting left, 0 is moved into the rightmost position. Another question you may have is, does the shift left instruction pass power or not? Well, it does pass power if the bit that was shifted out of the leftmost position was a 1. If the bit shifted out of the leftmost position was a 0, then it doesn't pass power. Next, we'll show you what's happening graphically. At the top, we have the bit pattern for the input variable, and then we're shifting that input variable or those bits to the left, and then 0 into the rightmost position, and we're shifting a value out of the leftmost position. At the bottom is the output variable after we perform the shift. You can see that our rightmost position contains that 0 that was shifted in. Because we shifted out a 0 from the leftmost position, we're not going to pass power flow to indicate that the 0 was shifted out. Next, let's look at a shift right. Here we just shift the bit pattern in the other direction. We still have an input variable containing the bits to be manipulated, and we have an n input, which is how many positions we're going to move. This time we're moving 0 into the leftmost position, and we're shifting out the bit in the rightmost position. The rules for power flow are the same. Looking at the diagram, we're shifting everything in the input variable to the right. We're shifting in a 0 all the way to the left, and we're shifting out the rightmost position. The output variable is shown at the bottom, and since we shifted out a 1, we're going to pass power flow. We also have rotate instructions where we can rotate left or right. These are similar to the shift instructions. The only difference is that you don't have a 0 that you're shifting in, and you don't have a bit that you're shifting out. It's completely self-contained. Let's look at the bit pattern. In the case of a rotate left instruction, everything gets moved to the left, and then the leftmost bit gets rotated around to the rightmost position. So we have the input variable at the top, and then at the bottom you can see the result after we shift everything to the left, with that leftmost position rotating back around to the right. So there's no loss of data here, and from a power flow standpoint, a rotate instruction always passes power flow. So some of you who have used shift registers before from other PLCs may be wondering, are these bitwise operations really shift registers? Well, they're very similar, but not exactly the same, as they have some limitations. They only operate on full word or double word variables, so you can't manipulate a portion of those variables, and you can't shift in a value like a traditional shift register. However, with the OCS, you have some additional instructions that we'll look at, such as the element shift, or what we call the multi-shift, that have the characteristics you are likely used to with your other PLCs. Now let's look at the element shift, or what's also called the multi-shift. First of all, it can operate on bit type variables, byte type variables, word type variables, and double word type variables. The multi-shift instruction doesn't have a separate instruction for left and right, so you'll see there are more parameters that need to be filled in for the function block. However, it's very straightforward. The source for the multi-shift instruction is the location of the data that's going to be shifted. Typically, that's a variable-based array of the appropriate type. If you have a shift register of bits, then it'll be a variable-based array of bits. And if you're shifting around words, it'll be a variable-based array of words. The source is the location of the data to be shifted. The length is the number of elements in your total shift register. The number, again, is the number of positions we're going to shift. Again, that's usually 1. The direction is a variable. If you want to shift left, you put an always on, or a variable with a value of 1 in that field. If you want to shift right, you put an always off, or a variable with a value of 0 in that field. Your input is the variable that is going to be shifted into the first position, and the output is a variable where the data that is shifted out is going to be copied into. So any data that gets shifted out using the multi-shift instruction goes into the output variable. Let's look at what an element shift instruction could look like when I've configured it. So at the top center, we have a simple shift register that's based on word type data. The source is a variable-based array called weight with a dimension of 4. Here I have weight 0, 1, 2, and 3 from right to left. So the length is 4, and I want to shift 1 position. I have always on in the direction field, which means I'm shifting left. My input is the data I'm shifting in, which you can see on the upper right hand side. My output is the variable that is getting shifted out of the shift register, and then my result you see there at the bottom, with everything shifted over from right to left. The leftmost position, or weight sub 3, was copied to the output variable, and the input variable was shifted into the rightmost position of weight sub 0. So that is an element shift instruction when we're shifting left. Now let's look at what happens when we shift right. So I've drawn the input variable and the output variable on opposite sides. The input variable is now copied to the last position, or the leftmost position in the shift register, and the value in the rightmost position is shifted out and is copied to the output register. At the bottom you can see what things look like after the shift. We also have element rotate, which can be useful as well. This is completely self-contained. Just like the multi-shift, you have a source, a length, a number, and then also a direction variable that allows you with the same function block to either shift left or shift right. Here's what the element rotate instruction looks like graphically. So if we are rotating left in this case, everything moves from right to left, and the leftmost element of weight 3 gets copied around to weight 0 because of that action. Now let's look at some real-world applications where the shift register instruction could be useful. Our first example is a conveyor application. Here we have a motor controlling the conveyor, and there's also an encoder connected as well. Every time that motor does 1 revolution, the encoder also does 1 revolution. And every time that encoder does 1 revolution, a marker signal turns on. In this example, the linear distance that the conveyor belt travels with every revolution of the conveyor is 1 inch. And in our application, we are detecting when packages are present on the conveyor. So approximately 192 inches later, we need to turn on a zapper to zap any packages that are present. However, we don't want that zapper on when there are no packages present. So to accomplish that, we'll use a bit type or boolean type shift register. The shift register's contents are going to represent the marker ticks that exist from the package sensor to the start of the zapper. As mentioned, there are 192 of those marker ticks, so our shift register size is 192 bits, where each bit represents a marker tick, and we're going to shift left. Our input to the shift register will be a package sensor value of 1 or 0. So if a package is present when a marker tick comes around and a shift is performed, then we'll shift in a 1. And if on the next tick of the conveyor that package is still present, we're going to shift in another 1. So we're not just detecting the leading edge of the package, we're detecting the entire time that the package is present. At the other end of the shift register, when those bits fall off to the output variable, if those bits are 1, that will turn on our zapper relay. If those bits are zeros, then our zapper relay will turn off. Now let's demonstrate this application in Cscape. I have configured Cscape for this application I just described. Here is our shift register. Whenever that input is on, the shift register will perform a shift. Again, in our case, we only want to shift once every time we get a marker tick, with every revolution of the encoder, which tells us we've traveled an inch, so we don't want the conveyor marker signal from that encoder to go directly into the shift register. Otherwise, if it's on for more than one logic scan in a row, we're going to do multiple shifts when we only want to do one. So essentially here, we're creating a one-shot based on the conveyor marker to ensure that every time that marker turns on, we get exactly one shift into the shift register. Let's look at how we configure that shift register. So here we have a variable-based array called marker ticks. I'll open the tag browser and you can see that it's a variable-based array with 192 elements from 0 to 191. We're going to reference marker ticks 0, which is the first element of that array, as the start of the source of our shift register. The length is 192 bits, because we selected a bit type here. We'll shift one position and we're shifting to the left, so we put always on here instead of always off. The input to the shift register is the package present sensor. The output from the shift register 192 bits later is our zapper relay. So if we shift out a 1, our relay turns on, and if we shift out a 0, our relay is off. So that's the setup. Now let's see what that could look like on the OCS. Here is a reduced version of the application we just looked at. We had 192 ticks or elements in our shift register representing the distance between the package sensor and the zapper equipment. To show this clearly on the screen for this demonstration, I reduced from 192 elements down to 16, but it still works in the exact same way. So here is our conveyor, which is sitting here running, but there's no packages currently on it. So I'll simulate adding a package to the conveyor. You can see I have 3 consecutive ones going by, meaning that package is 3 inches long if we have 1 inch per tick. As that package moves its way down the conveyor, those ones are moving their way to the output and turning the zapper on, and then when they're done, they're turning that zapper off. So I'll send another package here that's a narrower one, and then I'll send another one that's wider. As you can see, I have ones that are shifting down with every tick of the encoder as that conveyor runs. Then, at the appropriate time, I'm turning on my zapper, and it comes on and stays on for the duration of the package. So that's very straightforward. Now let's look at another potential application for a shift register. This time we have a level sensor type application where we want to average a series of analog readings to get a better reading to work with from a control standpoint. Let's say we have a sensor that's monitoring the water level in a tank, and because of turbulence or waves or something like that, we want to take the average of the last 10 analog readings to get a result that we're happy with. For this, we can create a shift register with the last 10 analog input values from our sensor. Since we're doing some averaging, we'll use real type variables. The source will be an array of analog readings with a length of 10 because we're looking at the last 10 readings. We'll shift one analog reading in at a time from the current analog reading, and we get a new reading with every scan. We're shifting to the left, meaning we're shifting from a lower to a higher numbered member of our variable array. In this case, the output that falls off the end of the array isn't important. We're only concerned with the last 10 values, and that output variable is going to contain the 11th value. However, we still have to configure it. So here's how we're setting up that multi-shift instruction in this example. We're using real type values, and our source is an arrayed variable of 10 values, which represents the real values of the last 10 analog readings. We're shifting in our latest analog reading with every scan, and again at every scan we'll look at all 10 of those values and create an average. So let's look at this in Cscape. So here is my analog averaging application. Here I get new analog readings every scan to shift into my shift register. So I don't need to worry about using a one-shot. It's okay to shift in a new value every scan because I have a new value to shift in. So I can use always on here. As you may know, the analog values come in as integers to the OCS, and if we want to create a shift register full of real values, we need to convert that analog reading to a real value before we shift it in. So let's look at our shift register configuration. Our source is a variable-based array called readings with 10 elements, which you can see here. We always reference the first member of the array if that's where our shift register starts. It's 10 dwords or 10 double words long, and keep in mind dword or double word just references to the length of the data, not the type. Double words are 32 bits, which is appropriate for a real or floating point value. We'll shift one position at a time, and again we're shifting left. The value we shift in is going to be this real value of our analog sensor reading. And then the output value is the oldest reading or the 11th reading, which we won't be using here, but we still have to configure it. So that's our shift register configuration. Next we need to calculate our average. First of all, we're delaying the first second that the controller is running because for the first second after power up, we don't have 10 good readings yet from our analog sensor. After a second is done, everything has stabilized, and now we have a shift register full of 10 values. Then I have a math expression which is summing all 10 of the readings that are in the shift register for that scan, and then I can divide it by 10 to get my average. Now let's see what that could look like on the OCS. Here I'm showing all 10 elements of the shift register. Remember, we had 10 consecutive floating point values, and those were just conversions of the 0 to 32,000 analog values coming directly from the analog input. So here are the 10 individual elements. We're shifting in a new value from the analog input that's converted to real every scan, and we're recalculating our average from the last 10 conversions. Then I have an engineering unit conversion that counts over to feet. I'm going to manipulate this particular analog input on my I/O simulator to show the water level going down quickly. But as you can see, we have stable engineering readings, even though we do have some bounce in the individual conversions into the analog cart. So that concludes our demonstration for today. Thank you for joining me for today's tutorial, and the Q&A session will begin shortly.
Okay, so there we have shift registers. Seeing them working with both analog and Boolean values, so hopefully that was very useful. I don't see any questions coming in, so let's have a look now at the upcoming webinars. So what have we got? So 18th of the 8th, the one we've just had, Cscape shift register instruction. The next 2 weeks, we've got a pair of videos that handle retrofitting legacy OCS. So they're for people who've got OCS 100s, 200s, old equipment basically. How are you going to upgrade moving forward if you want to move to an XL or an X series product? That'll take you through all the steps required to do that. The week after that, we've got the X5, a truly unique all-in-one controller. So we'll be looking in a lot more depth into the X5 and using that particular controller. And then on the 15th of the 9th, we've got OCS in a 12 volt DC environment. So probably particularly applicable to people who are putting it on outdoors equipment where 12 volts available, such as machinery, vehicles, etc. So how do we go about operating an OCS in that situation? So thank you very much for attending, everybody, and we'll look forward to seeing you next week for the Retrofitting Legacy OCS Part 1 webinar.